is Paola Cascante-Bonilla. She's a PhD student in the Computer Science Department at the University of Virginia. Her research lies at the intersection of natural language processing and computer vision, and she's going to talk with us about generalized zero-shot learning via normalizing flows.
Thank you. Hi, yes, I'm really interested in using fewer labels for large-scale recognition. So yes, in this work we explored the generalized zero-shot learning task using normalizing flows. And this work has been under the supervision and advice of Professor Vicente Ordóñez, who is now at Rice University, and also under the collaboration and advice of Professor Jianyun Shi from University of Virginia. So let's start. Deep learning models have pushed forward significant progress in many computer vision tasks for specific datasets and benchmarks, where all data is drawn from the same distribution and all classes are known on training and test time. And these models are remarkable accurate and on the image classification task, and usually we use a lot of annotation data. So for example, this is an image of my dog and my cat. So if I want to train a system or a model that accurately classify them, I may need to show them a lot of pictures of dogs and cats. Now, if I increase the number of available classes, let's say 5 classes, all animals, dog, cat, lion, tiger, elephant, and I input the dog and in a well-trained model, okay, I get a good accuracy on the dog. In fact, this is a dog. Also for an elephant, even higher accuracy for an elephant. But then if I input this animal, the model won't know what to do, and the accuracy will be all over the place, and the class, because the class is not even there. So what can we do? How can we generalize the to unseen classes? For example, if I have these 5 training classes, then what if I want to test on salamander, giraffes, zebras, right? So annotating data is expensive in real world scenarios. So new images from previous unknown types may appear, and typically these models are unable to make a correct prediction because the systems are trained ignoring the existence of such classes. So what is zero-shot learning? In computer vision, zero-shot learning refers to the task of recognizing images for which classes are not available during the training time, but other data, for example, textual descriptions or attributes for all classes are available. For example, here I may have a lot of images of cats and tigers, and I have all this text, for example, flexible body, strong, flexible, quick reflexes, small praise. It has retractable claws referring to cats. Then muscular body, right? And then it also has claws, but the body has shades of brown and orange with white ventral areas and destructive vertical black stripes and so on. Tiger. Now, if I add these other 2 extra captions, lizard-like in appearance with slim body, moist, without any scales, no claws, right? And this other is okay. This is a tiger salamander. What is a tiger salamander, right? So it has characteristics of a tiger salamander. Salamander is like this one, but a tiger then is like this one tiger. So it has 4 legs, small eyes, large mouth, long tail. So if I give you all these descriptions, you may be able to actually, a human, generalize and say, okay, I kind of know what is a salamander. I know what is a lizard. I know what is a tiger. And maybe the intersection of these 2, somehow I can say, okay, this is, it has the same characteristics of this other one. But it's a little bit different, right? So in the zero-shot learning, this setting, the system is able to generalize from the seen domain, which are all the available text, and the visual domain, which is like the unseen images, right? So yes, okay, this is a salamander, and this is the name of this strange animal, axolotl. It's a Mexican salamander. It's quite nice and interesting if you have never seen it. Yeah, you can Google for it. So the idea is to leverage this information, and this is in fact a more realistic scenario for image classification problems, where it's not possible to manually collect and annotate all the images for a specific class. But it is easier and more possible and viable to use natural language descriptions because they are for free, and you can go and scroll and scrape Wikipedia or get a lot of textual descriptions for not only animals but also objects, scenarios, etc. So in a more formal way, the problem setting, you have these scene classes. We have all the labeled images during training, which is this X images and YS corresponding to the labels of a set of M scene classes. Then I have the on scene classes, which are N. Let's say I have N, and this set is disjoint from the scene class, so it's completely separate. The labels for these images are not present during the training phase. Now, we have access to this auxiliary information, which are descriptions or semantic attributes for both seen and unseen classes in training time. And we may have like semantic embeddings A for all the set YS and YU, right? The seen and the unseen. Okay, and then we also have different setups. We have the inductive zero-shot, transductive zero-shot. The inductive is more like the classical approach. Here, I don't have access. I only have access to the images that are labeled. The transductive zero-shot, I have access to the unlabeled test set. So to minimize the bias towards the seen classes, because if you train a classifier, it might be a little bit biased towards what the classifier had seen instead of generalizing to the novel classes, right? The conventional zero-shot learning and the generalized zero-shot learning that we are referring to today, which is harder to train because to test because you are testing on both the unseen and seen classes. And in previous work, it has been done like feature alignment. So they try to model the relationship in the image space through a transfer function that uses the text attributes to shape the seen and unseen classes representation through a feature alignment of the embedding space. So let's say these points are just my images. These are my text. So you can see cat, lion, tiger usually are pretty close. Elephant and dog are more like out there. So here the objective is to map the image features and semantic attributes into the common embedding space. So then, for example, for testing on unseen images, you can basically get this embedding space and typically compute the nearest neighbors, do a nearest neighbor search in the semantic attribute space to find the closest match and then label those samples. Now, other methods have used generative methods, such variational autoencoders, generative adversarial networks, basically to generate new images that can be then trained along with the other the scene images to train a classifier. So this is basically conditioned on the attributes, and you basically sample from the, like, for example, here in the GAN, the generated condition on the attribute, and then you can kind of generate new images and then train the classifier. Our approach is more about normalizing flows, which is a series of functions that are invertible, or the analytical inverse of the function can be calculated. So this is a pretty nice property, this bijection. So typically in model, you get the input at the output, and but there is not a one-by-one correspondence, let's say. So using normalizing flows, you can actually have like an invertible neural network where you extend your output to a latent space Z, and then you can have this bijective property. Which is nice about normalizing flows in invertible neural networks is that they are easy to train, they converge faster, and it's more the hyperparametric tuning is not that difficult as with GANs, for example. So this is our approach. Here we have the images. We go and extract the features out of the convolutional neural network, typically like ResNet 50. And then you have like the text. Here we have full text, so we pass it through a recurrent neural network. We have the latest last hidden state representation, and then we try to map those to the classes, and then we extend the latent space, and we try to minimize the distance between the latent space of the two representations. So maybe a better a description of this. Here I have the image features, ResNet 2048 features. We have the text features, 312. The vector representation of those. So we have two invertible neural networks. We try to map them, so we have a little bit of supervision to the classes. So remember the images, we have all the scene classes, which are in this setup just 160. And for the text, we have all the classes for the text, so we have 200 classes. And then since we are mapping them and trying to make them invertible, right? So we have this latent space drawn from which follows a Gaussian distribution. So the goal is to minimize the distance between these two spaces by computing a metric loss, like MMD loss, so that the two distributions are really close. And then we basically sample for free a lot of generated features from this to train a classifier, and we actually get pretty good results. So this is in the COP dataset. We have this COP dataset has 200 classes. This is only birds, and using our approach, we get an improvement, significant improvement over other generative models. So here you can see that U is for unseen classes. This is at accuracy 48.61. The seen class is 55.52, and the harmonic mean, which is the per class accuracy. What's next? Well, this is ongoing work, so we are still exploring a lot on this. So we basically want to also test this on other benchmarks, traditional other data sets, such as the animal with attributes. It has the animals and the attributes like black, white, brown, stripes, water, eats fish or not. And then the sun data set, which has 397 categories. There are also other attributes for all those categories, and those are scenes, indoors, outdoor scenes. So the good thing is that zero-shot can be not only applied to classification, but also you can get novel object detection and, of course, image retrieval. So thank you so much. If you have any question, or comment, would be great.
Thank you, Paola. Michelle, are there any questions from the audience? Otherwise, I've got some questions. Well, I'll start while she's looking at that. So you mentioned at the very end a noun data set, and I'm curious, does this work? Are there certain types of data that it works best at? Is it animals? Is it nouns? Like, how about nouns versus actions?
Yeah, that is a really good question. That I think the spirit of zero-shot learning is more about, okay, I could annotating images is really expensive, right? So humans may take a lot of time, on effort, and money to pay people to annotate them. And text is free. It's like there's a lot of text out there, and it has a lot of also corresponding classes, for example. So here we are showing results in COP, the COP dataset, which is a really challenging dataset because all the animals are birds, but for sure this can be used on animals, places, objects, on scenes, on any type of images, because it is really rich, the text and information that is out there.
So you mentioned rich text. How complete does that text need to be? Can it be a sparse phrase? Does it have to be 3 sentences? What are you looking for? Have you seen a difference depending on the quality or the quantity of the text you have?
Yes, actually, you can see the differences in the quality of the text. For example, if you text Wikipedia text, for example, even for this COP dataset, you may get enough information and very rich information to actually get a good classifier in the very end, as opposed to only have a few scarce attributes, maybe like the animal with attributes, which all of them have like the same attributes, and then it's just like a yes or no,
Wow.
like is it does it eat fish, yes or no, and so on. So yeah, the larger and but also, I mean, Wikipedia is really rich because it has a lot of descriptions and a lot of data, but maybe there are not such rich descriptions in other type of texting in on the internet, but or out there. But in general, the more seems to work better.
Okay, thank you. Okay, I think we're out of
Okay,
time, but I want to thank all of our speakers, Corinne, Shin, and Paolo, for very interesting and fascinating talks.